Hi all, welcome to cbse.com. Now in this video we will learn about the types of the non-ideal solutions. In our last video we have discussed there how a non-ideal behavior in an ideal solution is different than an ideal solution. But right now I'm going to discuss only about the types of non-ideal solutions. We actually have two types of non-ideal solutions. One with the positive deviation and the other one is the negative deviation. Right? So a non-ideal solution showing positive deviation from the Raoult's law and the non-ideal solution showing negative deviation from the Raoult's law. Because we know that we have learned in our last video that non-ideal solution does not obey the Raoult's law. Now let's try to understand it with some examples. In a positive deviation, suppose here if you take water, let's suppose I have a solvent here which is water, and in the water I'm going to add here the ethanol, C2H5OH. In the solvent molecules, when you look at the different water molecules, in the water we have a hydrogen bonding there, correct? Between the two water molecules there is a strong hydrogen bond, okay? But once you add ethanol in it, so the hydrogen bond will break down between the solute and the solvent, between the two solute molecules, and a new hydrogen bond will be formed there between solute and the solvent. Now once you make a solution, once you add ethanol in it, so ethanol molecule C2H5, right, OH, it can also interact with the water, it can also form the hydrogen bond, but the force of attraction here between the ethanol and the water is weaker than what you find between the two solvent molecules, right? Suppose here we have water here, and if we say this is the A interaction, and now this is the AB interaction, right? Solvent A and the solute is B here. What we find here, once you add ethanol in the water, the force of attraction between the solute and the solvent is weak than what you see in the solvent molecules. So that means here in this case, in this particular example, AB interaction is weaker than A interaction, right? So obviously when you add a solute in the solvent and the force of attraction between the particles in the solution is weak, and therefore the vapor pressure will be more. So vapor pressure of a solution will be more than what you expect as per the Raoult's law. So graphically we represent like this, this is the vapor pressure, this is the vapor pressure. Say this is the component A here, XA, and let's say this is the component B here, XA here is 0, XA here is 1. So this is the partial vapor pressure, and this is the partial vapor pressure of the A, and this is the partial vapor pressure of the B. So as per the Raoult's law, you can expect the vapor pressure of a solution should be like this. But here in this case, the solute and the solvent molecules have a weaker intermolecular force of attraction. That means the vapor pressure of a solution will be more, because vapor pressure depends on the intermolecular force of attraction. Once you add ethanol in the water, the force of attraction between the solute and the solvent molecules is less, and so therefore the actual vapor pressure of a solution will be like this. It will be more than what you find, what you expect actually here. You expect it like this, but the vapor pressure of a solution will be like this. Actual vapor pressure will be more than what you expect, right? This is as per the Raoult's law. This is the partial vapor pressure of A, and this is the partial vapor pressure of B. So for the components also, it will be more than what you expect. This is the partial vapor pressure of the component A, and this is the partial vapor pressure of the component B. So that means in a positive deviation, when you add a solute in the solvent, intermolecular force of attraction is weak, the force of attraction between the solute and the solvent molecules is weak, and therefore the vapor pressure will be more than what you expect as per the Raoult's law. So for this type of a solution, vapor pressure will not be like this. Vapor pressure will be more than what you expect. So that's why this is the positive deviation. When you add acetone if you suppose add acetone in ethanol, between the ethanol molecules there is a strong hydrogen bond, but once you add acetone in it, the force of attraction between the acetone and the ethanol molecule will be weak. It will be not so strong than what you find between the ethanol and ethanol molecules. Therefore, it will show a positive deviation. Vapor pressure of the solution will be more than what you expect. Now with a negative deviation, it will be the reverse, right? Suppose you have some solvent molecules and the force by attraction between the solvent is weak. Let's say here an example of acetone, right? Suppose we have an acetone molecule here. Acetone is our solvent, and we know that between the acetone molecules there are weaker forces of attraction. Van der Waals forces are there, okay, and they are weak. But if you add in the acetone chloroform, CH3C, CH3Cl, chloroform. So once you add chloroform in the acetone, chloroform and the acetone molecules will have a stronger force of attraction. Okay, the force of attraction will be much stronger than what you find between the acetone molecules. It's because that in the chloroform, the carbon is attached with the electronegative atoms, 3 chlorine atoms. They'll pull the electrons from the carbon, and the hydrogen here attached to the carbon will attain some significant positive charge, and that positive charge will interact with the carbonyl group of the acetone here, and now the force of attraction will be stronger. So once you add a chloroform in the acetone, the force of attraction is strong, and when the force of attraction between the particles is strong, vapor pressure will be less, because we know that vapor pressure depends on the intermolecular force of attraction. Vapor pressure is inversely proportional to the intermolecular force of attraction. So that means in a negative deviation, right, the force of attraction between the solute and the solvent particles, AB interaction, solute and the solvent interaction, is stronger than what you find between the solvent and the solvent molecules, right? Therefore, here in this case, the vapor pressure of a solution will not be that you expect as per the Raoult's law, right? Rather, it will be less than what you expect from the Raoult's law. It will be like this. This is the vapor pressure of a solution, right? And same thing will happen with the partial vapor pressure of the solutions of the two components. And same thing will happen with the partial vapor pressure of the A and the B. So it will be like this. This is the partial vapor pressure of A, and this is the partial vapor pressure of the B. And the vapor pressure of a solution will be equal to the partial vapor pressure of A plus partial vapor pressure of B. So that means in a negative deviation, when you add a solute to the solvent, the force of attraction is stronger, and therefore the vapor pressure of a solution is less. Hope you got the concept. Thanks for watching the video. Bye for now.